Hello everyone and welcome back for another video of Love in Deep Space. Today's video is a special video because this time we're gonna talk about the behind the scenes of Love in Deep Space. So Infold just released an in-depth article sharing the latest technical insights behind Love in Deep Space. There's in this article they will be talking about the behind the scenes stories, creative processes, and lots of valuable details about how the game is made. So if you are interested in those kind of things, then this video is for you. So the article is actually in Chinese on this website, which they shared it with me. They still did not make an English version of it, but it will be released soon. So, Love in Deep Space first deep technology sharing review. As a surreal 3D interactive mobile game, since its launch on January 19, 2024, the number of players worldwide exceeded 70 million, winning the best mobile game at Cologne Game Show 2025. Today, Unite Shanghai, 2025 event, engine engineers from Love and Deep Space for the first time to share in-depth technology to reveal the creation of Love and Deep Space. How to create a real and sensible world for players through the film-level rendering pipeline, real and delicate physical effect. So this is a scene full of seats, which it is one of the Unity conference in 2025 that they made a more better zoom in on it. Unfolding paper, which I think they mean Infolds, and paper games. Sharing and creating is the norm in our work. In the past year, Paperwork held nearly 40 internal sharing sessions. The total number of employees participated in the total of 5,000 times, of which technology sharing accounted for more than 50%. Sharers come from various production group and technical departments, covering practical experience and frontier exploration in different directions and providing an open atmosphere for free flow of professional and ideas. Here is the full review of Love in Deep Space technology sharing. So, in short, I will be summarizing all of this. So, the rendering framework of Love in Deep Space focuses on three main parts: scene rendering optimization, lighting and pipeline design, shadow optimization. During development, the team built a custom SRP, which means scriptable render pipeline, by deeply modifying Unity 2019's engine. The current Android version uses GLES 3.1 and a Vulkan version will come later to make the game look better and run faster. In the scene rendering optimization, they made a special rendering system called Render Group Renderer, where each group of objects to draw is called a render group. This system adds several improvements. 1. Custom static scenes. They removed game objects, which reduced the slowdown caused by updating many objects. 2. Faster CPU to GPU data transfer. They cut down how often data, like instance data and constant buffer, is sent from the CPU to the GPU. At first, they used a pre-made buffer for small indoor scenes. Later, as the game grew and needed more detail, they moved these tasks to the GPU for faster performance. For more info about constant buffer optimization will come in the next section. 3. Better multi-threaded processing on the CPU. For static, non-moving objects, they used burst plus job system to process them in parallel, improving speed. The CPU does only basic cropping while the GPU handles the more detailed parts. Instance data. In most games, instance data information used to draw many similar objects is sorted in a constant buffer, but this method has problems. It has a 64 kilobyte size limit. It can cause cache issues that slow things down. It doesn't work well when using dynamic indexing, accessing data by variable indices. Another option is using SSBO, shader storage buffer object, but that also has issues. It's slower than constant buffers when caching works well. Some Android devices can't read SSBOs and the vertex shader, especially under GLES. Both methods still rely on dynamic indexing, which hurts performance on low-end phones. Their new solution, new bottle of old wine. They introduced a new method called vertex stream based instant data. How it works? They use a vertex stream, which means per instance step, as the instance buffer. This avoids dynamic indexing, improves cache hit rate, and keeps good compatibility. The computer shader writes data directly to the instance vertex buffer, achieving GPU-driven rendering, less work for the CPU. Unity engine modification. Because Unity doesn't natively support per-instant vertex streams, they modified the engine, added a custom draw mesh instance and traditional function in the comment buffer. This function uses another mesh as instance data. They also added tools to define how each piece of instant data connects to vertex attributes. In short, they replaced traditional instance data methods with a custom GPU-friendly system that runs faster, avoids cache problems, and works well even on low-end Android devices. So, in this part here, GPU-driven rendering system, which they built a GPU-driven rendering system to make the game faster by letting the GPU handle more of the scene processing instead of the CPU. So how it works, from pre-allocated buffers to pre-calculated offsets to object into buffer, which means before rendering they prepare some things. Then on each render group has a preset instant offset stored in a parameter list, as we can see here. They only use one shared instant buffer, which keeps things simple and efficient, and they also make another buffer that stores info for every object, as you can see, I think, in this picture here. Then we have the CPU calling. So before the GPU does its work, the CPU first checks which group of objects are likely visible. It starts from a big bounding box. If the combined box is too large or includes 4 apart objects, it's split into smaller boxes. The system compares volumes and uses PVS data to skip whole groups that are definitely invisible. This step is important because unlike DirectX 12, their engine can't completely skip draw calls on the GPU, so the CPU must filter out as much as possible first. We have the GPU calling, clipping. The GPU then does more detailed checks for each object. Con calling, load calling, high-Z occlusion calling, which means the con calling checks if the object is facing the camera. The load picks the right level of detail based on distance. High-Z occlusion calling removes objects blocked by others. We have the shadow elimination. To speed up shadow rendering, they use a technique inspired by Dragon's Dogma, where a shadow receive mask is used. If a shadow volume doesn't touch any visible areas, it skips, saving performance. In short, they build a smart GPU-driven system that preloads data, use both CPU and GPU to remove invisible objects, optimizes shadows, and focuses on making each draw call as fast as possible, especially for mobile devices. Now, in single draw call performance optimization, which the developers found that most rendering optimizations focus only on reducing the number of draw calls, but that's not always the best approach. What really matters is how much CPU time each draw calls takes. So this is like, there's a lot of informations here, which I will just skip them and just tell you what they are talking on it in short. These are all the info so far here, which we have PSO switching optimization, buffer submission optimization, rendering logic optimization, RHI call optimization. You can read them if you want, but in short, they prove that optimizing how draw calls work is more important than just reducing their counts. By reorganizing shaders, buffers, and rendering logic, they made the game run 3 times faster on the CPU, even with the same number of draw calls. You can see here a picture of the things. I think if the people who work on these softwares, they will know, they will understand. And here we have other optimization attempts, benchmark scenario test results, which in short, new features like MDI showed good results. Bindless didn't perform well yet, but the render group system still achieved big gains, cutting CPU and GPU time by more than half overall. Now, for the lighting plan. So in the lighting plan, they forward rendering pipeline. The team chose a forward rendering system instead of deferred rendering for several reasons. First, it's better for artistic flexibility, more mobile friendly, which is the most important for us, than GLES compatibility issues. So there were issues using Unity default system, which only support 4 lights per object, which isn't enough for large scenes. What they did is they made a method that keeps lighting stable, predictable, and helps developers stop lighting overload problems early. As you can see here in this picture, they divide the world into a grid tiles in front of the camera. Each tile is 2 meters wide. Each tile supports up to 4 light sources. The system uses a 125 and 125 index map to store light info. So for the Vulkan version pipeline improvement, for the upcoming Vulkan version, they added a sub-pass-based light pre-pass system to improve lighting speed and quality. The rendering flow, if we go here, we have the pre-Z pass, light volume pass to shading pass, motion vector, vegetation example, full Vulkan pass order, which all of those help in the rendering flow, but there were some limitations, like light pre-pass only replaces the default lighting model. For complex lighting models that need more GP buffer channels, forward plus is still required. However, they added an optional per light parameter that can for standard lit mode, so one tile can be affected by more than 4 lights with slightly less accurate lighting. As for the GI, which is a global illumination, they used the traditional light map plus light probe system. The light map stores indirect lights only, as we can see here in the picture. Light probes can use multiple sample points per object, not just one, for smoother and more realistic lighting. So the point of this is to make things give more realistic variety. Like the result of all of this is when many objects share the same reflection probe, reflection still look different depending on their positions and lighting. So they wanted to make it as surreal as possible. It depends on what I understood, which in short, they used forward rendering for flexibility and mobile performance, added a tile-based lighting system for better control, and built a Vulkan pipeline with smart light pre-passes and data reuse. For GI, they combined light maps, multiple points light probes, and enhanced reflection probes to achieve realistic, as I said, efficient lighting on both old and new devices. So as for the shadow optimization, which we have like functional design, distance elimination, penumbra region detection, which we can see here, and the picture, two picture, that is what we see and this is what they see. That's what they do. We have the pixel by pixel bias. The following figures show the comparison between fixed bias and pixel by pixel bias, which I'm not sure what is the difference because both look the same. So in short, for this paragraph, the shadow system uses 3-level CSMS plus character and pre-object shadows, all combined into one screen space shadow mask, which is RGBA for shadows and AO. It applies a distance calling to skip for shadows, penumbral detections to limit high resolution filtering only to soft edges, and pixel by pixel bias, this one, to reduce light leaks and self-shadowing. A scrolling cached shadow map reuses previous frame data to boost performance with future plans for local shadows, atlases, and dynamic precision control. So now for the this part 2, which I don't know what it's written, but in this part, which they speak first about the character lighting scheme. Okay, these are some steps or type of problem that they face. Then there is like 3 kind of requirements which are also in Chinese. So in short, with all of this, if you want to read them, I will just scroll it little by little. So in short, the character lighting scheme, aka the characters get customized lighting, main light, contour light, and extra spotlights. So here we see that, for example, every character has his own light. Okay, we can see some more info, more specific info. So here is an example, the light effect that can be connected as it follows. So as I said, characters get customized lighting. Indirect light uses separate probes for scenes and characters. Reflections and special materials can use custom probes. Lighting templates are saved and managed for easy switching. real-time updates and plot animation control. Here, for example, the following picture is a project-specific plot editing tool. Basically, all lighting and shadow related parameters and some post-processing physical effect can be controlled in this plot editor. Here's a more zoom in on it. So all of these are things that we cannot see behind the scenes. And this one, as I said, when they work only on the character itself, other than the behind the scenes, or let's say the place. So first we spoke about the character lighting scheme. We also have here a close-up shadows. This also is separate. So the summary of this, uses a small shadow map around the character for precise shadows. As you can see here, we have Raphael. Combines with the main cascaded shadow map for each pixel, and parameters like distance, light, and biases are adjustable for better control. See? So not only the character by itself, but also when there is a close-up shadow. Then we have the skin details. The skin details, which, for example, we have the blushing effect. We also have the sweating effect. So not only these, but these are just example. For example, we have the blushing effect, hand-drawn masks and curves control natural area-specific redness. So all of these have some specific process, like they have their own things, their own steps. Like it's not something that how to explain it. Like it have an option which they work only on, for example, the blushing effect, the sweating effect, which shader and particle effects simulate moisture with masks and auto-driven parameters for realism. So everything that we see, sweats, blush, or maybe when they are angry, all of these have their own points or things that they work on. These are just some examples on the details or the codes. For example, here we have sweat effect of sports companionship system. So this is kind of a layer that they work on, other than blush, other than the shadows, and other things. Now for the part 3. So in the fabric simulation implementation, okay, which we have, they work on many things. So this is the things that they use, like why using bonds instead of proxy grids. Okay, that's what they use. So the point of it is to give us a natural effect, something that will make the clothes, the hair, everything to behave naturally and easy to tweak, for something more stable and realistic. As you can see here, for example, the specific effect can be referred to the performance of latest decor. When we see them in game, we see that they are their performance is very natural and not something like, it's as if they are real persons, if you want to say it like this. We also have, for example, here, see the points that they use on the clothes, for example. So here on the clothes, they use bond-based XPPD simulation for stable and realistic motion. So when we move with the dress, we see it as it's moving naturally and realistic. We have his collisions which use BVH, mesh colliders, and spatial hashing for efficiency. Also, the Kosrat road constraints make clothes and hair behave naturally and are easy to tweak, as we saw here, and we saw the hair here. Look at the hair, how it's moved naturally. Even the clothes, here for example, see. So the interlayer collisions and penetrations are handled with lightweight frame-by-frame fixes. Here we have the face. So the system is designed to give realistic close motion while still running well on mobile devices. It works smoothly with complex scenarios like battles, plot scenes, hair, and layered clothing. See here the ones that we spoke about. See how the movement of the clothes is moving so natural. So the close simulation, which bonds as particles with, like we said, XPPD plus substeps for stable clothes. Then we have the constraints, which Koseret roads give natural bending shared with hair. We have the close character connection, which is hierarchy for rigid areas, adsorption for flexible joints, collusion handling BVH plus cached pairs, Fesh maze collider for complex shapes, interlayer collusion, which is spatial hashing and spring fixes for layered cloth. This is a layered cloth. And the sixth last one, performance, which is realistic cloth with stable mobile friendly performance. Now for the real time performance control. So we have here which one is cutscenes tracks. Most physics effects in Love in Deep Space are controlled via cutscenes. Custom tools allow artists to adjust and regulate physical effects precisely, as you can see in this GIF. We have the smooth blend pose track. We also have a pose track. Anyway, for the smooth blend pose track, which reduces jitter when switching action by interpolating between initial and current poses. See, when we change from a pose to another, plus adds small time overhead but greatly improves smoothness. We have the pose track. Oh my god, look at this scene. So in the pose track, it saves physical states offline for complex cut scenes and directly applies saved states to close for perfectly smooth performance, which means they applies saved physical states offline for smooth cutscenes performance. We have now the edit param track, which allows real-time modifications of clothes physics parameters, softness, damping constraints, can create special effects like breathing clothes. So as you can see in this, we can see how how they are breathing. So in the edit param track, real-time adjustment of close physics parameters for effects. We have the animation track, which combines animations with physics for complex interactions. So to ensure collisions and movement are realistic even with engines or rig differences. And this GIF, which shows the interaction between the necklace and physics and animation, including the state switch from physics to animation and the switch between different animations. So it's combined animations and physics for realistic interactions. So for the collider track and wind track, which here, for example, if you want to read this, which dynamically create or destroy collision bodies and wind fields during cut scenes. It control affected objects via layers, types, or cloth. Fine-tune parameters per frame, size, direction, intensity, turbulence, and etc. Which, in conclusion, it works on dynamically manage collisions and wind fields with per frame control. So, in short, with all of this, they are trying to make it as much realistic as possible. Everything in the game, if you see here, this is what we see and this is what they see, I think. See the difference? They work on everything, not on just one thing. The GIF is some example for orbital capsules and wind fields. Same here. This is what we see and this is what they see. Also here, the same thing. See the behind the scenes? Wow. So now we have the 3 development based on Unity dots. So I'm not sure even if I read this, if I will explain correctly, as I have no info or I don't know anything about Unity and how it works, but I will try my best. So as you can see, we are seeing just behind the scenes of some codes that they work on. Okay, and on conclusion, first here, this is the 3 look. So they work on optimizations and the project to further improve performance. And of course, for it to work on all of the devices and for us not to have any issues, which we can see the hard work they put behind the scenes. So we have jobs, birth, and mathematics, which in short, this means physics built in dots, simulating more than 2,000 bone particles. So all of these are just like small particles that we cannot see in details, which make this scene. Okay. Then we have the cache job, which reuses jobs each frame to reduce main thread stalls. This is just like a picture of how it works. Execute, atomic queue, empty, array, empty, execute job. We have the neon intrinsics, handwritten ARM SIMD code boosts performance. So this boosts performance. These are codes. And for we have dot and the transpose, which both of them optimized vector and matrix operations for faster computation. So I think this, instead of us seeing it very slowly, we can see it like moving fast. That's what I at least understood. And these are some stuff they used. So lastly, we have collision detection module. So the first is widely developed from Unity's major physics modules. Unity's default physics modules exist, but Love in Deep Space needed is independent layer settings for different gameplay, because we do see that in the game there's a lot of different gameplay. Custom trigger exit logic for combat, and better performance for collision only detections via dots. Now, for the implementation's futures, which basically the native collision queries fully implemented, custom update and trigger logic, and thread-safe query interface, lightweight dots structures give 15% performance gain. This is like an example. So we have ACE-H, and the example of query processes, the ACE-H AH-based dynamic BVH for broad phase collisions acceleration. I literally have no idea what these are. Okay, the people, the developers, maybe the people who use Unity or know about Unity will understand this. We have the memory allocated per thread, 4 threads on real devices for efficiency, and accuracy slightly reduced to simplify algorithms and improves speeds. Now, example of trigger processes. We have special enter-exit trigger system for combat, as we already said it. And we have ensures, which ensures triggers appears in pair even when colliders are removed. And they also uses history counts to avoid logic conflicts from overlapping triggers. So this is like a small pictures on how they do. Frame input, collider A, trigger enter B, remove collider B, blah, blah, blah. So in short, custom physics is needed, independent layers, combat triggers, and dot performance. The futures, native queries, custom triggers, thread-safe interface, 50% faster with dots. We have draws phase and memory, SH-based, BVH per thread memory, simplified algorithm for speed, and trigger logic, inter-exist triggers, paired, handles, removes, uses, history count. So in short of all of this article, okay, they showed us on the things that they work on, which is they work on the character lighting. We have some close-up shadows. So not only they work on the character itself or the background. So the background, they work on it alone. The character alone, even the close-up, either it was the shadows or the skin details, all of this, they also work on it like layer by layer, okay? And they also do their best with the real-time performance, which also, like for us, when we want to play on every device, so it can work on everything, on every device, so we can have smooth scenes, okay, They also spoke about the unity dots, their job, the burst, and some collusion model. I have no idea what is collusion model, which I think it's like it's a system that have layers, triggers, and optimized performance. Yes. So all of these they shared with us. I hope you have watched until the end. Thank you for watching and hope to see you in my next video. Bye.